Okay, so before we start, I just want to run through a couple of things that you should be doing to make sure that you can concentrate on the session. If you've got a mobile phone with you, turn it off, even better, put it in a different room so you don't get distracted by any messages or just that temptation to have a look. Similarly, if you've got any other tabs open on your computer, on your browser, close those down just so that the only thing you've got open is what you're focusing on, the work and this video. Please answer all the questions. Try. There'll be moments when I'll ask you to pause the video, and so you can press pause and you can answer the questions, and then press play again, and we can review some of the work you're doing. And similarly, if you need to, you can always rewind and listen again if you're not quite sure what to do or you want to listen to an explanation again. And finally, and I think this is just good advice generally in life, don't give up. If you find something hard, listen to it again, have another go, think about it, and please try to answer everything. So this activity is about forces and representing forces using force diagrams. Here are some questions about forces that you may already know the answer to. When I stop speaking, press pause and see how many you can answer without looking at any notes. Press pause now. Here are the answers to the first two questions. How did you do? Correct any mistakes and add any missing information. Press pause while you do that. So, just to sum up those answers, it's important that you know that a definition of a force is a push or a pull that occurs when two objects interact. So we always have forces when there's more than one object and when one of those objects is being pushed or pulled. And then there are many examples of forces, and these are the ones that we will use in the next few sessions. And in this session, we're going to concentrate just on a few of these. So up thrust, normal contact, weight, friction, air resistance, water resistance, tension, thrust, and magnetism. And I will explain what those mean as and when we meet them. Here is the answer to question 3. So again, correct any mistakes, add any missing information, and press pause while you do that. Okay, so hopefully the first two of those questions are pretty straightforward. Force B is acting upwards, force D is acting downwards. You can tell that by the direction of the arrow. And I think a very important point, but I hope you've all noticed, is the longer the arrow, the bigger the force, and the smaller the arrow, the shorter the force. And so if you wanted to show a decrease in the force, you'd make the arrow shorter. And that's a really important point, and one that we'll return to again. So now we'll look at drawing force diagrams. We can't see forces, but we can describe them. As you saw in that last question, we represent forces using a force diagram. Each force is represented by an arrow. This means it has a direction. So the bigger the force, the longer the arrow. This means it has a size. So all forces have both a direction and a size. So our diagrams must show that. Now when we draw forces, there are some rules that we should use. So all forces should be drawn from the point which they're acting. Forces act in pairs. The direction of the force should be clear from your arrow. Arrows of different sizes showing the size of the force. And those arrows should be drawn from a central point. So we don't need to draw the object. We put a dot in the center of that object and we draw our arrows from there. And each force has a name. As you can see here, we've got 4 names. Lift for the force acting upwards on the aeroplane, pushing it up. Thrust, pushing it forwards. Weight, pulling it down. And air resistance, acting against the thrust. So you will often see pictures of objects, but we don't need to draw them. So we'll just put a dot in the center of the object, or even just put a dot on its own if there's no object already on the sheet, and draw our forces from there. Now, different forces have different names, and we're going to look at 5 of them that we're going to use when we draw our own force diagrams. First, we have up thrust, and 2 things to know about this is it always acts up, that's why it's called up thrust, and it always acts on an object in water. It doesn't have to be floating, it can be submerged in water, but any object that's in water will have up thrust, and obviously any object on Earth anyway, if it has a mass, it will have weight. So we see an example here, a ball on water has up thrust pointing upwards and weight pointing downwards. It's called gravity here, and you can sort of use those interchangeably, but I think it's better to use weight, and that's what we'll be using in this lesson. So the other force we'll be using is tension. If an object is hanging from something, like a piece of string, then the weight is balanced with tension. Okay, so tension is a force acting against the stretch in a string or rope. So anytime you see something hanging from something, that can be a string, a spring, something that you're holding with your arm, there will always be tension in whatever it is that's holding up the object. And obviously weight will be acting in the opposite direction. Okay, now similar to up thrust, we have a thing called normal contact. So unlike up thrust, where objects are in water, this is when an object is resting on a solid surface, and it's just like up thrust, it acts upwards, but we call it a normal contact. It's sometimes called a reaction force, and you can use either of those terms, but in this lesson we'll call it a normal contact or normal force. And finally, if 2 objects are rubbing against each other, the force that goes in the opposite direction to that movement is called friction. So friction always acts in the opposite to any force that is trying to move an object along a surface. So you can see here the person is trying to push the wardrobe along the ground. So the pushing force is pushing it forwards, and the force of friction is acting in the opposite to that. So let's draw a force diagram to show what we mean. Make sure you have a sharp pencil, a ruler, and a rubber, and some paper to draw on. Ideally that would be graph paper, but don't worry if you don't have some. A page from an exercise book is fine. So if you need to, pause the video and go and get yourself a sharp pencil, a ruler, and a rubber. Okay, so you're going to need at least half a page for this diagram. And I'd like you to draw your version as I draw mine. And if you make any mistakes, pause the video, rub out your mistake, and then press play again. So you can see here we've got the aeroplane that we saw earlier on, and the forces acting upon the aeroplane with different size forces in each case. So the first thing we're going to do is we're going to turn this into what we call a free body force diagram. And what that really means is we're not going to draw a picture of an aeroplane, we're just going to draw a dot to represent our aeroplane. So there it is, draw that in the middle of your page. And then using a ruler, I would like you to draw the lift and weight arrows. So the lift arrow, I'd like to be 9 centimeters going upwards. So the point of your arrow to the dot should be 9 centimeters. And the weight arrow should be 6 centimeters from the dot to the point of the arrow. If you need to, pause the video, count the squares. It's 1 square per centimeter. And once you've done that, we're then going to draw the thrust and the air resistance. So the plane is speeding up, so the thrust arrow should be bigger than the air resistance. The thrust arrow, that's the arrow going from left to right on your screen. The bigger one is 13 centimeters. So you should be measuring out an arrow that is 13 centimeters long. And the air resistance, just to be a little bit more tricky for you, is 8.5 centimeters, so 8.5 centimeters. You can see it's 8.5 squares from the dot to the point of that arrow to represent the air resistance. If you need to, just pause the video while you're doing that. So what you should have is a dot in the center and then 4 arrows looking just like that with 1 centimeter for each of the squares that I've got. Then what we need to do is label them, and that's pretty straightforward. I've already talked about them. We've got them in the diagram there. So if you need to write next to your arrow pointing upwards, lift, the arrow pointing to the right should be thrust, and the arrow pointing downwards should be weight, and the arrow acting against thrust is called air resistance. If you want to, you can just call that drag. Okay, so having drawn your own version of a free body force diagram, I'd like you to have a go at drawing your own from these examples. So again, as we did, draw a spot in the center to represent the center point of the object. You can do that on the sheet if you printed that out, or you can just draw that as a dot on a piece of paper in your book. And then use a ruler and a pencil to draw the arrows to show the direction that the forces are acting in. And based on the information I've just given you around the types of force, I'd like you to name each force. The final three, G, H and I, they're a little bit more challenging because the forces are going to be acting at sort of slightly different angles. But again, have a think about what you think they would look like and have a go at those if you can. Use this slide to help you name the forces. They're just summarising the forces that we've talked about. And once you've done the first two diagrams, you can press play again, and I will just run through what they should look like and talk to you about the kind of rules that we should be applying, so you can then see how you're getting on. Okay, so press pause and have a go at the force diagrams. Okay, so here are the first two, just for you to check for yourself whether you're doing it right. Couple of things for you to look at. Firstly, have you drawn a dot in the centre? If you haven't, you should. Make sure you've obviously used a ruler and a pencil for your force arrows. They should always be straight. Don't draw them freehand. And in the cases of all of these examples, each arrow in the pair should be the same length. If you haven't done that, you should adjust them just to make sure that they are. We'll talk a little bit later on about what they look like if they're different lengths, but at the moment they should all be the same length. And then have you correctly named the forces? So in this case, the duck is up thrust and weight, and tension and weight in the case of the plasticine ball. Okay, so hopefully your diagrams look like those, and if they do, please go on and have a go at the rest of the sheet and compare your answers with what we talked about here. And then if you need to get further guidance, then obviously you can send your work back to your teacher, who can let you know how you've got on with the rest of the diagrams. Okay, so this next activity looks at measuring forces and a concept that we call in science that we call resolution. So we can measure forces using what's called a Newton meter. So it's just a hook and a spring, and we hang an object off the spring, and that gives us a sense of how much weight it has. But we can also use that to drag things, and that can give us a way of measuring the force. And the unit that we use to measure force is called the Newton, after Isaac Newton. So 1 Newton, 2 Newtons, 3 Newtons would tell you would be a size of 3 different forces. Now, some Newton meters will give what we call a more resolute reading than others. So what does that mean? Well, it's all to do with how small a measurement it can make. So let's look at what we mean by that. So the smallest possible measurement of a piece of equipment is called the resolution. So I'm going to show you on the next slide 2 Newton meters. And what I'm going to ask you to do is to look at that and ask yourself what has the lowest resolution, and also what is the resolution of each. So just to illustrate what we're talking about. So here we have 2 Newton meters. Newton meter A, which is the blue one, that measures from 0 to 10 newtons. And Newton meter B, which measures from 0 to 1 newtons. And look very carefully at the numbers down the left-hand side of each newton. So the question is, which has the lowest resolution, and what is the resolution of each newton meter? So I'm going to ask you to pause and have just a little think of it, and then I'll show you the answers. And just a little hint for you, think about what the smallest line would represent for each newton meter. So press pause and have a think. Okay, so here are the answers. So I'll just explain what they mean. So the answer firstly was B. B has the smallest resolution, or the lowest resolution. But let's start with A. So A has a resolution of 0.2 newtons. It measures, in other words, it measures to the nearest 0.2. So each line on there represents 0.2 newtons. And just in case you're not sure what we mean by that, if you look there, the numbers go from 0 to 10. And if you see between 0 and 1, so between 0 newtons and 1 newtons, there are 5 lines. So each line represents 1/5 of a newton. A bit like on your ruler, there are 10 lines usually between 0 and 1 centimetre, so each line represents 1 millimetre or 1/10 of a centimetre. Here, each line represents 1/5 of a newton, which is 0.2 newtons. So we would say the resolution of that newton metre is 0.2 newtons. Now, on the green one, the one on the right, you have to look very carefully. It's quite difficult to count because they're quite blurry, but there are 10 lines between 0 and 0.1. So each line represents 1/10 of 0.1. That's quite a tricky bit of maths to do, but 0.1 is 1/10 of a newton, and 1/10 of a tenth is 100th. So each line represents 100th of a newton. In other words, 0.01 newtons. So you can see that newton meter is able to measure a much smaller difference, if you like, in force than the blue newton meter. Now, don't worry if you didn't work out what those numbers meant. The main thing is if you were able to spot that the green one measured to a much smaller resolution, in other words, a much smaller force difference. So each of those lines represents a smaller number of newtons compared to the blue one. Now, if you're able to spot that, then you do essentially understand what we mean by resolution. Okay, so what I'd like you to do now is find the resolution of different measuring equipment that you'll find around the house. So, for example, you may have a clock on your oven that will measure to a certain amount of time. There will be a ruler, which hopefully you've been using already in this lesson, or a tape measure, bathroom scales, a watch, any clock indeed, or even a thermometer. And what I want you to look for is what is the smallest unit that it can measure to, and I want you to write that down in a table. So, for example, you've got a ruler. It presumably looks a little bit like this, where it's measuring, in the case of this one, to 1, 2, or 3 centimeters, and each of those smaller lines represents 1 millimeter. So we would say that the resolution of that ruler would be 1 millimeter, because that's the smallest unit it can measure to. And what I'd like you to do is to record your results on a table in your books like this. So see how many you can find, and add any that I've not mentioned that you have at home. And don't forget to give a unit in each case, and that will be different from one thing to the other, because obviously clocks measure time, rulers measure length, and the unit for time and length are obviously different. The next task for you to do is to find out about Isaac Newton, who is famous particularly for his work on forces, but also for a whole host of other aspects of science. So there is a research Isaac Newton sheet that your teacher will have shared with you. I'd like to use that to find out some key facts about Isaac Newton, and to find out the answers to each of the questions on that sheet. Finally, there is a home experiment that you can do just so that you can see the effect of forces in the case of water. So we're talking about upthrust. Just have a read through this, follow the instructions, and yeah, see what happens. Thank you.